Alright, here's your brief integrity recording to cover some of the disaccharides that were not covered in class time. The comment after the end of activity 11 was about hydrolysis of an acetal, which is the linkage that holds together a disaccharide. If you add water to break something apart, that's called hydrolysis. In the case of acetals, it requires an acid catalyst, and you simply result in forming the simple monosaccharides from a disaccharide if you hydrolyze it. There will be phosphate esters mentioned later. I'm not going to dwell on those at the time being. They're important to carbohydrate metabolism, but you will recognize the ester as the POC linkage when you cite it, as mentioned back in chapter 17. Okay, the important disaccharides that you need to be aware of are three. The first one is maltose, and it is simple to recognize if you remember glucose, because glucose has that up-down pattern, and if you have two glucose molecules with an alpha-1,4 linkage, we call that maltose. It is a product of the breakdown of starch. If you hydrolyze it, you can get this disaccharide. It is called a reducing sugar because it still has the hemiacetal on the right here, so the answer to that question is yes. And it is described as being able to mutarotate. Mutarotation is something I didn't discuss in detail in class either, but that means that it has the hemiacetal and could switch between the alpha and beta forms. We will see the starch that it comes from when I get to the polysaccharides. Disaccharide number 2 is lactose, and its components are suggested in its name because it's glucose, as in all of the disaccharides they include glucose. The second one is galactose, and the linkage here has got to be a beta-1,4 linkage. The structure at the top is taken from your text and is clearly showing the beta orientation on carbon number 1 of the galactose. It has to be the galactose in that anomeric carbon that's in the linkage, and then carbon number 4 of the glucose that is connected to it. Again, as I mentioned in class today, if you have carbon 6 and 4 and 3 in this six-sided ring as up, 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 that is a recognition of galactose. The same thing is evident on the structure at the bottom. Up, 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 3 in a row of the up orientation, and then the next one is down. That makes for galactose, as opposed to glucose, where you have up, down, up, and down, and the last one is up if it's beta. So that's glucose on the right, galactose on the left. They're both shown in a beta orientation. You need to know that the galactose is in the acetal linkage. That's why it's called a galactoside. Oside means it's got an acetal. All right, is this one a reducing sugar? Well, a reducing sugar has to have what present? A hemiacetal, as hopefully you recall from activity 11. And there it is. There's your hemiacetal, an ether and an alcohol on the same carbon, namely this anomeric carbon of the glucose on the right side of the disaccharide. Disaccharide number 3 is sucrose. Sucrose is our ordinary table sugar. It's isolated from our friends the sugar beets that are commonly grown in this area of the country in the Red River Valley. So that's what they're isolating from those funny things that are bouncing all over the streets in the fall. The structure of sucrose is a weird one. It has glucose on the top and fructose on the bottom. They're both D sugars, as evidenced by their CH2OH from carbon 6 being up, but they have different orientations. The alpha is what the designation is for glucose, because that carbon on the anomeric carbon, the group on the anomeric carbon, is pointing down, and it's beta for fructose, because the anomeric carbon of fructose, which is here, has the OH, or the alcohol group, now reacted to make an acetal pointing up. So this one's beta, and the upper one is alpha. So those are two anomeric carbons connected together, so it's a 1 and 2 carbon linkage. That's carbon 1 from glucose, carbon 2 of fructose. Fructose, again, looks a lot like glucose because it has an up, down, up pattern to the OH groups and groups on the ring if you start from carbon 6. And so in this case, there is no hemiacetal linkage because you have the anomeric carbon of glucose connected to the anomeric carbon of fructose. Neither one of them has the hemiacetal remaining, and so there are two acetal linkages. One of them is with the glucose and the oxygen bridging the two. The second one is with the fructose and the oxygen bridging the two. In this case, this is no longer a reducing sugar, no hemiacetal present. All right, now the last part you could read in the text, but I'm making a recording, so I'll show you a few slides and let you know a little bit more about the polysaccharides that are of interest in this chapter. There are three major types of polysaccharides. They include cellulose, starch, and glycogen. So let's begin with cellulose. Cellulose is the most abundant structural framework in plants. It is what is fiber in the diet. It's good for our digestive tracts. It is glucose combined in beta-1,4 glycoside linkage. Glycoside simply means that it has an acetal present. And so glycosides are what holds together all of the disaccharides and polysaccharides. So beta and 1,4 linkage is different from the ones we were looking at in the disaccharides so far. And only cows and termites can digest this, not humans. We don't have the proper digestive enzymes to do that. The structure of cellulose has a couple of diagrams in the text for you to look at. It has a beta-1,4 linkage, which on the left over here should be evident to you. It's pointing upwards on carbon 1, and so that's beta, and it's 1 and 4 between these two sugars. If you remember what glucose looks like, it's up, down, there's a down, up, and down. So that's glucose on the left. The second sugar, oh, this one looks really funny. You can't really identify it from that structure, so having this pointing down here makes no sense to us. We're not going to be able to make sense of that diagram. The one on the right is more helpful. So up, down, and the last one up being beta. And then the second sugar has up, down, and up. Oh, but this is just a disaccharide. So this is a disaccharide that comes from cellulose because it's got the same linkage as cellulose, beta-1,4, between two glucose units. So there is a disaccharide that you don't need to know, but it's simply a fragment from cellulose. Carbohydrate digestion, as a comment, is going to require hydrolysis of these disaccharides or polysaccharides down to monosaccharides by hydrolysis in your stomach or in your mouth. Generally, they all hydrolyze down to glucose because they all contain glucose. In your stomach and in your mouth, there's going to be enzymes, in your saliva included, and in your stomach, you're going to have acid provided as well. And it goes on into the small intestine to break down into the monosaccharides that are going to be processed for various metabolic processes. You don't need to be worried about the details here. Maybe another class will give you more information about that you need to know, but not today. Okay, and so cellulose is hydrolyzed by enzymes that humans do not have. We do not have an enzyme for beta linkages. We only have the enzymes for alpha glucosides. And so the beta linkage of cellulose makes it undigestible. Consequently, it's what we call dietary fiber. It simply slides on through the digestive tract and exits at the opposite end, not having been digested or broken down in any significant way. So if you have a beta-1,4 link, it's not digestible. If you have an alpha-1,4 link, well, then that's a different story. So the stereochemistry of the alpha and beta linkages is entirely relevant to our digestive processes. Enzymes are going to only be able to do certain kinds of things. We'll tell you later. One of the buzzwords is they are very picky. Okay, polysaccharide number 2 is starch, but it has two types. And the two types of starch have similar looking names. These are plant products. One is amylose, and the other one is amylopectin. Name is similar, but they have A's in their name to remind you that they are going to have alpha linkages, and they're all alpha-1,4 glucosides in the linear polymer of amylose. So you have a bunch of these connected in a linear fashion with alpha-1,4 linkages. Don't expect to have to sort one out from a picture. I think you can recognize that as alpha-1,4, but it might not be your favorite way to recognize one. The fragment at the bottom of this slide shows you just a segment out of an amylose molecule with the alpha 1,4 linkage between glucose monomers again. The second type of starch is called amylopectin, and it's much like amylose, but it is branched. So what else is new? It has an alpha 1,6 linkage, which makes it unique. There's carbon 1 and carbon 6 of these two sugars being connected by an alpha linkage. Alpha because this is pointing down on the anomeric carbon from the top sugar. So if you put together two types of linkages, alpha 1,4 and alpha 1,6, then it becomes amylopectin, a branched structure, one of the two types of plant starch. These are going to be digested by an enzyme called alpha amylase. So we can digest this. Alpha linkages are digested by an enzyme. Enzyme endings are ASE. Alpha amylase digests alpha linkages in starch, not in cellulose. There is no alpha linkage there. Here's a diagram that represents the structure of amylose. That linear structure can coil around, and this is why when you do the starch iodine test, iodine situates itself in the center of this sort of helical arrangement. It gives you the blue color known for the starch iodine test. Okay, here's a couple pictures of disaccharides just to contrast the two. Cellobiose has the beta 1,4 linkage, comes from cellulose. Maltose is the one we need to know, the disaccharide that comes from amylose because it's got alpha 1,4. So here's alpha linkage, and there's 1 and 4. Cellobiose, by contrast, of course, then would be from cellulose. It would be beta 1 and 4 linkage between those two glucose molecules. The terminology at the bottom of the screen is just for your information, not that it's something I'm going to test you about. Just you might run into those thoughts. Okay, polysaccharide number 3 is glycogen. Glycogen is an animal starch. The previous two were plant products. And animal starch is going to have almost the same things as amylopectin, but it's got more branching. So if you look at these two figures from the textbook, it's, I think, the most informative. They look kind of like plant structures to my thinking. But the one on the left is the one from plants. It's called amylopectin. But in animals, glycogen has much more branching. A lot more little circles are shown in this picture for glycogen, suggesting very dense packing of glucose monomers into a small space. So it's got the same linkages, the alpha 1,4 and the alpha 1,6, just the same as amylopectin, but in a more dense arrangement. And so if you put those all together, those comprise our list of polysaccharides that you're going to need to know. So shorter changed, highly packed, and dense, that's glycogen. So which one is the polysaccharide that provides structure in plants? I hope you know which one it is. It should be our good friend cellulose. Enough said for the conversation about polysaccharides. Good luck with your studying, and I hope you all do well on the test.